A2 Maths, differentiation of a function of x in terms of y. Okay, so what I'd like you to do is I would like you, just starting with this equation just here, y cubed equals x, find dy over dx. You can use your normal skills like you learned from your first year just to find dy over dx. Okay, so I'll pause, give you a chance to work through it. Okay, so you know how to find the gradient function. You know how to find the gradient function as long as it's y equals. That's what we've looked at so far. So the first thing I'm going to do is just rearrange this equation and make it y equals. Now I could do that, as you well know, by taking the cube root of both sides. So I'm going to rearrange to make y the subject. And what do I get? There you go, the cube root of x. Now knowing the cube root of x is helpful because then I can change it to a power, which of course is to a power third, and then I can just use the normal rules of differentiation by bringing the power to the front and decreasing the power by 1. Then what I'll do just to finish it off is just put it back into this sort of form, back into surds, by writing it like that. Okay, so well done if you managed to get that. But the problem is it's not always that easy to rearrange. For example, if I just added something simple to this, like something like plus y cubed plus y equals x, then I wouldn't be able to rearrange it, so therefore I wouldn't be able to work out dy over dx. So there must be a more efficient way to be able to rearrange the equation so that you can find the gradient function. And we're going to show you that now. So grab your notebooks and just take down this first bit of notes. If you've got a function written in the form x equals some function of y, okay, so it's the other way around, x is some function of y, and you want to find dy over dx, so that's the bit that's a little bit different. Okay, normally you'd have y as a function of x, and it would all be fine because you'd have dy over dx. You differentiate the y function in terms of x. Now what makes this a bit more tricky is you're not looking for dx over dy. If you were looking at differentiating the x function in terms of y, it'd be very straightforward. What they're looking for though is still dy over dx. We're still looking for that change in the y over the change in the x. Okay? So what we can do is we can still work it out. We're just going to use the following rule. If I want to work out dy over dx, it's just going to be equal to 1 over dx over dy. I can literally just flip that fraction over and find the reciprocal of both sides. Right, so why does that help me? Let's just look back at that previous example then. So if I'm given x equals y cubed and I want to find dy over dx, rather than changing it and making y the subject, rather than making it y equals some function of x, I can keep it in this form. And the first thing I'm going to do, instead of working out what dy over dx is, I'm going to work out what dx over dy is. I'm going to differentiate the x function in terms of y. Now, although you might not have done that before, it's not any more difficult than what you have done previous. If I want to do dx over dy, I differentiate it as I would do normally. I bring the 3 to the front, I decrease the power by 1, because you're differentiating the x function in terms of y. Now then, that's not what the question asks though. The question's asking, what's dy over dx? So I could just finish this off then by working out what is 1 over dx over dy. To work out dy over dx, I can just rewrite it as 1 over dx over dy and find the reciprocal. And there we go, I've finished. If you want it in terms of x, which you wouldn't need to, have a look. What's y equal to? The cube root of x. Oh, but if I put the cube root of x in there, I get exactly the same answer as I had previously. Same answers you've probably got written down in front of you. 1 over the cube root of x squared. Okay, so keeping your notebooks out, let's have a look at this exam question. I want to find the gradient function of this, and I want to work out the gradient at the coordinates 7, 2. Okay, so I'm going to work out the gradient function first and then work out the gradient at this coordinates. Now you might want to just pause it and have a go yourself. I will show you the model solution when you're ready. Okay, so pause if you want to go yourself. Okay, so let's see what you would do. The first thing you need to do is definitely work out the gradient function. Now, because we've got x in terms of y, notice you cannot rearrange it and write y in terms of x. You can't do it. So you're forced to differentiate x in terms of y. And if I do that, dx over dy gets me 3y squared plus 4y, sorry. Once I've done that, what I can do now is I can work out dy over dx. I can work out, it says there, the derivative of y in terms of x. And what do I get? Dy over dx equals 1 over 3y squared plus 4y. It does not matter that this function is in terms of y. That is not an issue at all. There's nothing wrong with having a gradient function, dy over dx, in terms of y. In fact, later on, you'll have it in terms of x's and y's. There's absolutely nothing wrong with that at all. What do we do next then? Well, I want to work out the gradient at 7, 2. Notice I've got in terms of y. So what will I do to work out the gradient? I put the y value into this. So I'm using y equals 2. I substitute it into the function, and therefore I get 1 over 20. It makes no difference that I got the y value instead of the x value. I can still work out the gradient at that given point. Of course, then you could do other things. You could work out the equation of the tangent. You could work out the equation of the normal. Anything else like you've done previously. Speaking of that, have a go at this exercise on page 2.2, which is involving you differentiating a function of x in terms of y. Okay, one reason why it's quite a good idea to be able to differentiate the function the other way around is when you get out an equation y equals ln x. So grab your notebooks, let's just have a go at differentiating the function ln x. Now we don't know how to differentiate the function ln x, but what we do need to know how to do is differentiate its inverse function. And its inverse function is the exponential function. So the first thing I'm going to do is just rearrange and write it, instead of y as a function of x as a function of y. Once I've done that, I can then differentiate x in terms of y. So if I work out dx over dy, then I'm going to end up, as you know from differentiating the exponential before, you end up with exactly the same. Okay, so the exponential function does not change when you differentiate it. It has the same gradient function. Right, why does that help me then? Well, if you look at this, I can now work out what dy over dx is. Dy over dx is 1 over e to the y. And so that's the right answer. There you go, you're finished. But what's quite nice about this one is that e to the y is just x. So what I can do at the end is I can replace that e to the y back into x. And so dy over dx equals 1 over x. And so that fact you do need to know, you do need to learn, but you would use it a lot. That whenever you've got a function of ln x, if you differentiate it, it always goes to 1 over x. The gradient function of ln x is 1 over x. So make sure you've got that nice and neat in your notebooks, not just how to actually show it, but also making sure you've got that fact nicely highlighted because you will use it a lot. Okay. So what we're going to do is we're going to use some differentiation, same as what we've done before, but we're going to try using the chain rule. So we've shown how to use the chain rule previously. So let's have a quick look at this question. I want to work out ln of 3x squared plus 2x. So what I want you to do is pause it. I would like you to have a go at practicing your chain rule yourself, and then you can write it down nice and neat in your notebooks afterwards. Okay, so hopefully you did this yourself. Let's see how far you got. You're thinking about, because it's a chain rule, why do you have to use the chain rule? Because you've got an inside function and you've got an outside function. It's a function of a function. So the first thing I'm going to do is differentiate that inside function just there, 3x squared plus 2x. What does that differentiate to? So if I differentiate the inside function, I'm going to get 6x plus 2. My inside function goes to 6x plus 2. Once I've differentiated my inside function, I can then consider the outside function, ln u. What does that differentiate to? Well, that's the one I've just done. That's the one you've still got written in your notebook right in front of you. How do you differentiate ln u? It goes to 1 over u. Now then, once I've done that, I can just put these two results together to find me dy over dx, because the du's will cancel out, leaving 6x plus 2 times by 1 over u. Okay, so there we go. Du's cancel out. All I did there was just replace the u back to that part. So I end up with these two times together, and lo and behold, 6x plus 2 over 3x squared plus 2x. Okay, right. Reason why you've got this down in your notebooks is an important fact. If you're ever differentiating a ln function, just there, and using the chain rule, notice that your numerator is always the differentiation of the denominator. So whenever you're differentiating anything like ln of a function, you always end up with the function itself on the bottom, which is always true for the chain rule, the function reappears, and the differentiation of that function on the top. Now you might just think, can't I just differentiate using chain rule? Yes, you can. But why this is important is when we look at the opposite to differentiation, integration, later on. And we're going to be looking at noticing that the denominator differentiates to the numerator. Okay, so that fact is always true. If I'm differentiating ln of a function, then I always get a function on the denominator, and the numerator is always the differentiation of that. Okay, pause if you still need to take any notes. Right, so what I'd like to do is just have a go at completing the exercise 3.2, which is involving using things like the chain rule and the ln function before we move on.